Okay, welcome to R session 4. This is the last R session. After this, there are a couple of practical examples, but this is the last time we're going to be in R going through code together. The goal of this session is to give you a broad overview of your options. So we're going to talk about the different ways you can analyze pupillometry data. I'll share my thoughts on which ways I prefer. If you want to follow along in R, just like the last sessions, if you go to the R session folder, you can either select the basic script or the markdown script. I have opened up the markdown version of this script, which once again is going to mark the code chunks for following along with the PowerPoint. If you look in the example data for this session, you'll notice the directories are slightly different. In the pre-processed data section, we have some fully prepared data sets for analysis. We'll talk about each of them as we get to them. One of them is a published data set. One of them is a preliminary data set, which you've already sort of seen some snippets of. I also have a folder called plots and a folder called models. You'll notice that these are full. We are going to go through and generate what goes into these folders, but I gave them to you full of things in case your machine, for example, isn't able to converge a very complex model in a reasonable amount of time, which is very possible. So all of these, we'll go through it. These are going to be models that you can open and look at on your computer. So we've pre-processed data. We did the 2 stages of pre-processing pupillometry data. What do you do now that you have these nice, beautiful pupil curves? You have some options. As I noted yesterday, pupillometry is still a relatively new method. And I would say in the last 15 years, there's been a lot of change in the preferred analysis methods. And that is partially related to the general change in cognitive research and psychology research, moving from ANOVAs to linear mixed effects regression. So a lot of earlier papers that were using iLink and Toby technology, so by earlier, I mean like 2010, they will report statistics like peak pupil diameter and mean pupil diameter. And we'll go over what those mean. These are what I like to call summary statistics. The pupil response is a time course measure. We are looking at a change in pupil size over time. So if you want to gather the critical information, you might decide that what you care about is the peak, the absolute highest point in this curve. Or you might say you care about the mean size of the pupil during a certain window. And so these were strategies that were used in particular because researchers were using ANOVAs. And with ANOVAs, you need to summarize this complex time course data to single values per condition, per participant. I'm going to show you how I do summary statistics with linear mixed effects regression. I will not be showing you any ANOVAs today, but the same process of preparing data is exactly the same for these 2 methods, with one minor difference, which is that for linear mixed effects regression, we'll summarize data to the trial level, which you might not always be doing with ANOVAs because you can't have all of that. You can't have the best of both worlds. What are your other options? Curve fitting. Curve fitting is pretty cool. 2 of the most common approaches to this being implemented right now are growth curve analysis and generalized additive mixed models, which are called GAMs. Growth curve analysis is essentially the fancy version of polynomial regression. So if you've taken a stats class, they probably, at least for one small unit, took you through polynomial regression, which is how you can fit a time course of data and you can make your model quite literally fit to your data. Because typical linear mixed effects regression, as the name indicates, is linear. We have these straight lines. And if we're trying to model a curvy line, we can't do that unless we introduce polynomials into our models. Polynomial regression has one issue that comes up very frequently, which is an issue of collinearity. If you want more information about that, I'm going to refer you to a book written by Dan Merman about growth curve analysis, and how growth curve analysis is basically polynomial regression, but it reduces collinearity issues. So that's sort of the short of it.
What do you mean collinearity?
So if you imagine, we don't need to imagine, we can look at a plot. When we get to this section on growth curve analysis, when you're building a polynomial model, you're going to put in a linear term, a quadratic term here in green, a cubic term, for example. In typical polynomial regression, these aren't centered like this. So growth curve analysis, the big thing it does is it quote unquote orthogonalizes these. And this is essentially centering them so that in the time course, these are less highly correlated. And that's what introduces the collinearity issues. And so it's just the way these polynomial bases are put into the model. Yeah. Does that answer the question?
Yeah. I mean, those are regular polynomials.
Yeah, if you were to do a standard polynomial regression and you plotted what your polynomials were, they would not be centered like this. Yeah. Okay. The other one here, which we'll go over, generalized additive mixed models. They also let you do curve fitting. They are growing in popularity. I have minor expertise in this. So if you notice me a little bit nervous when I'm teaching that section, it's because it's pushing my statistical knowledge a little bit. But they're pretty amazing. You can fit any shape essentially with GAMs. That's like the big, huge benefit of them. Whereas with growth curve analysis, you can only fit what is called a polynomial basis. Meaning this nice shape we're seeing here, we couldn't have a sharp peak on the left and then a soft peak on the right. We could not do that with growth curve analysis. And so it's essentially the shape is much more restricted, to put in simpler words. GAMs have a lot more flexibility. Because they have more flexibility in stats, anytime you're giving yourself more flexibility, you have to penalize yourself. And so there are a lot of, and this is where I don't understand the deep level of the stats, but there are a lot of penalties built into GAMs because of all of the degrees of freedom we have to fit the shape. So that's just like one note on the really major differences between these two approaches. And the type of approach you use is really going to depend on your needs. And so we're going to go through all of them. We're going to talk pros and cons, and we're going to do it with real data. So overview of the first data set. You have seen me talk about this yesterday in one of the sessions. This is a paper of mine that was published in 2023. I didn't choose it for this section because it's my favorite paper I have ever done. I chose it because in this paper, we did multiple analyses on the same data set. So it's very nice for comparing summary statistics and growth curve analysis specifically. So you've heard about this study. This is a study where we wanted to see if breaks reduce these quote unquote fatigue effects. Wynn et al. Had said in their best practices paper that frequently taking breaks and chatting with a participant during an experiment would reduce these fatigue effects where the amplitude of the pupil response is going to decrease over the course of the experiment. And we wanted to, with data, really empirically demonstrate whether this was in fact the case and whether the type of break mattered. Because they had recommended chatting with participants and we were like, long-term, we don't really want to do that. We don't want to have to chat with our participants on breaks. So let's come up with a break that's just as effective was our intention. The study design here, it's a random assignment. There were 3 groups with about 30 participants per group. The control group does not get breaks. They're going to do 80 trials in a row. Every 10 trials for the other 2 groups, there are breaks. One group got chit chat. They talk with the researcher. The researcher sits there and says, what is your favorite color? So on and so forth for a minute. And it's painfully awkward. The other group plays with toys, quite literally toys. And the one that was the favorite of every adult who came to do this study was the kinetic sand, which is a mixture of like sand, Play-Doh. It's a delight. It was a crowd pleaser, which will be relevant to how the data looks. Within the trial, We didn't really go over this. The task itself within this session, when they're doing 10 trials in a row, what are they actually doing each trial? This is a speech perception task where we had, in this case, a 3000 millisecond baseline period where they're just staring at a cross on the screen in quiet. And wait, that is not true, actually. Sorry. This is a speech and noise study. So we actually have the noise start during the baseline, and then a sentence plays in the middle here, which if anyone's curious about that, I can explain in a bit more detail why we decided to do that. And the noise continues into this delay period. Then the noise stops and they are in their repeat period where we had them repeat aloud in this study, the sentence that they heard to the best of their ability, because they're in noise, so they're pretty hard to understand. So this is like a moderately difficult task. And I don't remember the number off the top of my head of how well people did, but my memory is going to take a stab at it and guess it was like 75% of words were able to be accurately perceived. So a fairly challenging speech perception task. It's the same exact thing on every trial. There is no other layer of conditions. There isn't an easy noise condition and a hard condition. It was just one level of noise, one task. And what we are interested in is the difference between these three groups who did the exact same set of 80 trials of speech and noise perception, but their pathway through this series of 80 trials is a little bit different. We're going to skip to the chase and we're going to see what the data is going to look like. So this is from the published paper. We have our three groups. On the top, I am showing you the results of our growth curve analysis. So we are going to learn how to do this analysis. What I am showing you in particular is the effect of trial. The effective trial is a continuous measure. It's a number 1 through 80. But for plotting purposes in this paper, we do plot it as quartiles. So the first 20 trials, I'm showing you the mean, and that's what first means here. The first 20 trials, the second 20 trials, 20 to 40, I think you all know what I mean. And we can look at this across conditions. We did another set of analyses because, as I was sort of describing at the beginning, this field has been changing, and pretty much all of the papers preceding ours were doing summary statistics. And so we were encouraged by a co-author and then also during the reviewer stage, strongly encouraged to do what everyone else had done previously, essentially. I don't think that will be the case moving forward, and I do not think it is necessary to analyze a data set two ways. So I want to clarify that. I am not suggesting you do summary statistics and growth curve analysis. I recommend you choose one and follow through with the analysis. Also, do not do two analyses and then pick whichever one gives you significant results, because that is not good science. But I will show you the fully transparent what we found, because what we find is not the same in these two analyses. And we do report that it is not the same, and it makes the paper a complete mess, which is why it's not my favorite. But it'll be a good case study for us to see how the same exact data set analyzed different ways can turn out differently. So let's get started. If you have your code open, the first code chunk should be pretty straightforward, what we've been doing before. There are quite a few directories this time. I'm going to have you have a directory for where the data is, the pre-processed data. So make sure you're in R session 4, looking at these pre-processed data sets, because they are fully ready for you to analyze right now. And of course, if you're on a PC, your directories look a little different. So take a moment to adjust your directories like you did for the previous section. And just as a note, I don't often use R Markdown, and apparently the way I do directories makes R Markdown very unhappy. So if you're running into issues, let me know, because in the last session, it didn't like the way I was doing my directories. So let's see. I think it did change my directory, but let's check. Yes. No, it's in R session 3 still. Okay. If you have a hard time and you're in R Markdown, if you're not in R Markdown, you aren't going to have a hard time with this. As you can tell, I typically write in just basic R scripts, and I tried to convert it to R Markdown. And that's where some of the little hiccups come in. So all I did here, because it was getting mad at how I was changing directories, is I copied the code and I just ran it in the console. And now it's pointing to our session 4 pre-processed data. So apologies if you're setting your directories. Hopefully it works better for you than it does for me today. Okay, so first chunk is just set up. We're all pretty familiar with this by now. Let's then load our first data set. So this is the McLaughlin et al. 2023 data set. The name of it, I just left the name from the Open Science Framework repository. It's PFM_E1 because technically there are 2 experiments. We're only looking at experiment 1. So I've skimmed over details from the second experiment for those who are curious about the paper. So we are going to be loading this time course data set. So go ahead and run these first 3 lines of code. And if you get more warnings, it's our markdown. Just copy the code down to below like I'm doing, and it should start to work for you. So once you have it loaded, you should be able to use the summary function to get a quick snapshot of what this data looks like. Are people up to this step, more or less? So I'm also going to open this data. We have 6 columns. We have our subject, which has been loaded as a factor, and we can tell because of it's recognizing that each of these is a factor level, which is good for modeling. If it did not recognize this, it would say something like character, and it would not give you information about the individual names. Trial goes 1 to 80. We have our 3 conditions. This is our random assignment. The chit chat group, which hopefully is straightforward, which one that is. Control, kinematic is the people who got to play with sand. Time goes from -500 to 4,500. 0 is the onset of sentences. So in this pre-processed data set I've given you, 0 is when sentences start. We have a bunch of different items. These are different sound files. So it's just showing you, this is called the Clear Speech Project. And so they're just sentences recorded. And so this is sentence 17, sentence 22, and so on and so forth. Every participant should have these in a different order because it's randomized. And then we can see we have pupil data, which is good because that's what we want to analyze. Is everyone up to this point? Okay, so take a look at your data if you haven't already, and then we can plot it. So this is a very basic plot. You'll get to see some more complex, prettier plots later on that you can, obviously repurpose the code for yourself. This is a very basic plot that I like to do when I am first analyzing a pupil data set to give me an idea of the shape of the data. And one thing I want to note about this is I purposefully, the first time I look at my data, do not plot my conditions. The reason for this is because I'm going to refer you to a paper that's in the recommended readings. It's Peel and Van Engen 2020. There's only one Peel and Van Engen, so the year doesn't matter too much. Which basically showed that when we select a window, so you can see, it's a little bit hard to see, but there's a gray box here highlighting a window of data. This is the section of the data that we are going to analyze. So this was, I believe, predetermined with pre-registration for this data set. But additionally, we do some checks to make sure, not in this section, but especially in the growth curve analysis section, we do some confirmatory checks to make sure that the shape of the data can even be fit with growth curve analysis. And you don't want this to be informed by whether or not it's going to give you significant results. Does that make sense? So we are not plotting our conditions because we do not want to bias ourselves. This is an area where we're trying to remove these researcher degrees of freedom in order to do better science, basically. For peak and mean selection of window, for this paper, our initial analysis was 500, is that correct? You can see the window because we annotated a rectangle. Okay, it goes from 300 to 3,500. That makes sense because of the delay of the pupil response. It's pretty standard to start at 300 when you're analyzing your data. We went to 3,500, and this was an arbitrary number that I believe we chose during pre-registration. During review, reviewers were like, that's weird, because as you'll see when we get to the growth curve section, we actually stopped at 2,500. And they were like, you need to match it across these two analyses, which was a reasonable suggestion. So just a very small note, the data, we're going to process it the way that I did the first time. So it's just a teeny tiny bit different than the final paper. It doesn't make a meaningful difference is the other thing. Like reviewers wanted us to redo it, so we did. It did not change the outcomes of the study. Okay, so we've looked at our data and we've selected a window. And just as a note, you can use this plot function. And what you could do if you were actually analyzing this data set and making decisions, you could move around this gray box as you so desire and see what it looks like and whether you think you're capturing the data. Note that this gray box, the height and the top and bottom is arbitrary. This isn't to say we are cutting off our data if it goes above 120. That is just for drawing the box. We will be cutting off our data only along this x-axis. But for example, when we get to the growth curve section, this is the window we selected. And the reason will be because that makes a very nice polynomial basis shape. So you may be shocked to learn that for this analysis, summarizing data down to peaks and means from that section of the data is actually extremely easy. We can use pipes from dplyr, and so that's what I'm doing here. Let me zoom in a little, it's a little hard to see. Oh, it doesn't let me zoom in. Let me scroll here then. So what we're doing here is we're going to take our time course data, and we're going to feed it into this pipe and do a series of operations. The first one is we're going to say we only want data that's greater than 300 milliseconds in our time window. This is us setting our time window less than 3,500. So this is us setting our window for analysis. We then want to group our data by subject, trial, and condition and item, because we're going to use them in our models. We have to include them here, or else it'll drop these columns from the data set. And then we are going to apply the summarize function. This is group by and summarize are from dplyr. So if it yells at you and says you don't have those functions, try loading dplyr again. We are going to get the max pupil diameter within that window. That becomes PPD, that stands for peak pupil diameter. These are pretty standard abbreviations in the literature. And then we'll get the mean pupil diameter during our window. So if we go back to our plot, for every single subject and every single one of their trials, we are going to get the value of the peak. The goal being, once we have those peak values, we can compare across our conditions. Does this make sense so far? Okay. Go ahead and run this. And then open up your peak and mean. And what you will see is subject 102 should go from trial 1 to trial 80. And then it'll repeat for subject 103. This is the setup you want for linear mixed effects regression. If you were doing ANOVAs, you would need to simplify it further than this, just as a small note. Trial in a lot of data sets is not the thing of interest in this study. It's actually the thing of interest. So this is like one of our main things. We're going to be looking at the interaction between trial and condition, which is our random assignment to one of the three groups. Let's take a look at what's going on in this data, because the goal of this session is transparency. I have some ggplot code that you can use to first make a mean pupil diameter plot, then a peak pupil diameter plot, and then a plot of the time course. And this is the goal of this is to illustrate a point, which is that the data is very noisy. If we look, this is plotting a box plot across all subjects, all of their trials, all of the values we have collected of mean pupil diameter in this data set for each of our three conditions. And there is a ton of variation here. We have already cleaned up our data, but it is safe to assume it is still not perfectly clean, because with pupil data, there's still going to be a lot of noise and a little bit of chaos. Let's look at the peak pupil diameter. Same thing, although maybe a little bit of differences in how much variation by group, which I don't believe is meaningful, but possibly. One thing to note, we weren't necessarily in this study looking for a main effect of condition, meaning we aren't necessarily expecting these means to be different. But it's reasonable to assume that if, for example, our intervention with the chit chat really reduced fatigue effects, we're looking at change over time. We're going to look at an interaction, in other words, but it could also affect the main group differences. And when you look at this, it's very clear that there are no main group differences. We should not expect them from our models. If we look at the time course for our first 4 subjects, and we plot every single trial of time course, this is what the real data looks like. And this is like Wizard of Oz. We are pulling the curtain. You're seeing behind it. When we plot our nice group means, we get these nice Gaussian sometimes looking curves. The reality is that we have a lot of variation. Some of this by trial variation is actually what we're interested in this study. So that's not necessarily a bad thing. We expected change over trials. But if it was perfectly change over trial, we would see it go from very, very dark to very light would be our prediction. And we're seeing there's a lot going on. And in fact, we can spot, there's one participant up here who's got something sort of crazy up in that upper corner. This is a good point for me to note that the way we prepared the data for MPD and PPD was pretty basic. It's pretty standard, but I've seen some, I review a lot of pupil papers. I've seen some people who prefer these summary statistics, and they take a much finer comb through their data. And that is what I would recommend. If for your purposes, you need to do MPD and, sorry, you need to do means and peaks for your data, you need to go through with a finer tooth comb. So I have seen some protocols for screening out trials. So this is something, again, researcher degrees of freedom. You need to make sure that you do not know what condition you're looking at. But you can screen every single trial of your data, and you can flag, for example, I would flag this trial and throw it out because that's not a typical response. I find this to be a bit arbitrary, and this is why I do not like it, quite frankly. I'm typically much more inclined to keep outliers. In other words, this is like an outlier process, which we come across in all of our research everywhere. Outlier exclusion is a tricky thing. It does introduce researcher degrees of freedom. So I'm just going to encourage you all now to, if you are doing some sort of by trial exclusions and searching for crazy trials that you want to throw out, you need to come up with a procedure that does not show you what condition you are looking at, so that you cannot, even if you have good intentions as a researcher, you cannot fall into the trap of excluding data because it's going to make your result go away. But so this is what the real data looks like. And so it's perhaps not too surprising that we're seeing all this variation, because we know there are some trials that are all over the place. Sometimes the pupil is below 0 for quite a while, and that's why some of these means are below 0 for quite a while. Marco.
Really,
Hmm?
do you know of any like prioritization method that accounts for the fact that we are getting a discrete sampling from the continuous pupil response function?
Can you explain that again?
We have fixed points like the
Mhm.
samples every blah, 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 blah.
Mm-hmm.
So we are not really getting the probability density function, but we are getting a mass function because we have already scheduled bits like every
Mm-hmm.
0.0. So so that means that the maximum point or the maximum of your actual continuous function may not be present within your discrete sampling. So I want to know if you have ever seen or have you ever, yeah, about like how to account for that, or we only run with the understanding that we assume that it's a continuous function.
Okay, I think I understand what you're getting at, but it doesn't ring any bells for me, which makes me think that it's not a common thing that is done at the very least. but maybe we should chat about it afterwards so I can get a better understanding of what you mean. This is, and this is where I don't think I'm understanding your question. This is just the raw data. We haven't done any sort of,
Yeah.
Yeah.
Like you get,
we can discuss more. Yeah, let's see. Okay, so this is our data, but what we're actually interested in for this data set is not just this main group effect, but we're going to be looking at the interaction. So we're going to switch in the next code chunk to, well, first, this code chunk is just some basic prep. And then we're going to start doing some models. I want to walk through the models with you, then we'll look at model fits on the plot. So this is some basic prep where I'm just making sure things that I want to be factors are factors and that I like the order of my levels. So if you're familiar with LME4, this will probably make sense to you, but essentially in my model, I'm going to be using subject, item, and condition as factors. And so that's the name for essentially how we're formatting our data in R. It has multiple levels. This function right here is because I have 3 levels. R will always default your factor levels to being alphabetical. And I'm going to be using dummy coding. I use dummy coding a lot, to be honest. And I want my control level to be my reference level in this dummy coding. And then this function will just confirm. So if I scroll down, so if I run this, what's going to be printed in the console is the number of unique subject IDs, and this matches up with the data that we collected. So this was a bit of a logic check for me to make sure I had the amount of data I expected. There should be 80 unique item IDs. There are 80 trials. I then set the order of my factor levels and it tells me, okay, they are ordered control, kinematic, chit chat. This means in a dummy coding setup, we are going to get model estimates that compare kinematic against control, chit chat against control. I also have here a selection of control functions that you can put into any LMER model. Sometimes LMER models do not like to converge. And you can set different optimizers, and this goes past my knowledge of understanding what exactly optimizers do. Does anyone actually know? Possibly not. Yeah, yep. I've used Bowickla for a long time, but every now and then, if a model doesn't converge, you can use a different optimizer. This is just telling it to try for a really long time. Like, don't give up, because R will give up. And you can tell it, keep trying to find the maximum likelihood solution. So we will not actually use all of these, but I just put them here because these come from an old stats professor who's like, these are my go-tos, and I've just copied them into every code I've used since. So it won't hurt to load them. Next up in code chunk 6, you can just load in these models. I will say the mean and peak models are not hard to run on any machine. So you do not need to read them in, but this is just a good opportunity for me to explain what the save and read RDS functions do. These are built-in R functions that can save your models. So if you didn't know this, this is great for reproducibility in science. So I highly encourage you to do this. Also, once you start running complex models that take an hour to converge, you want to save that because you don't want to have to converge it again. So I have already run these models. They are in your models directory. So you can load them in with these functions after you change to the models directory. I'm going to go ahead and load mine in. Now we're going to start looking at the model code. Here, this might be sort of redundant with some of your previous statistical training, but I'm just going to start at sort of basic training so that I meet all audience levels. When I do linear mixed effects regression, there are different strategies for the order you build your models, building bottom up versus top down. I do what my stats professor instructed me, and I think that's very common. You know, who taught you to do it influences the approach you use. So this is my approach, but it is fine if you had a different statistician teach you bottom up, always build from the bottom up or something like that. I always build a full model with all of my fixed effects of interest and no interactions, and a fixed effects, and then a model with all fixed effects and interactions. In this case, we care about condition and trial. So in LMER syntax, this is saying condition and trial are effects in our model. Anything that's in parentheses is going to be random effects. I'll circle back to that. The colon indicates an interaction. So here I am saying I also want to model the interaction. In this case, this is only one layer of difference between these two models. But if you have many interactions and things, I would usually build this out. And you'll see that when we get to the growth curve as well. Since in this case, there is only one interaction, we can actually do a log likelihood model comparison between model 1 and model 2 to test whether the interaction is significant. And so that is the ANOVA function, which I know can be sort of confusing if you come from an ANOVA's world. We use the ANOVA function to compare linear mixed effects regression models. So if you do this in R, I already have my models loaded, so I'm just gonna skip down to ANOVA. What you will get, first it'll tell you that it's refitting with maximum likelihood instead of random effects maximum likelihood. That's fine, that's standard. It'll show you the two models that it just compared. And it'll tell you the degrees of freedom difference between these two models because this is an interaction. It'll say 2 degrees of freedom's difference. This is our chi-squared value. So log likelihood model comparisons have become sort of the golden standard in our area of research at least. So you would report, when you are reporting this interaction in your final manuscript, you should report that in this case, it did not significantly improve model fit. And then you'd report the chi-square value and the p value is here, as well as the degrees of freedom. You should report that too. So that is telling us about the interaction and whether it improves model fit. And the answer is no, it doesn't improve model fit. But let's take a look at the full model summary also. So this is 2 different sources of information. I am going to zoom out a little bit just so we can see more of this model. So this is my model 2. So this is my full model. It has interactions in it. We see, because this is dummy coded, it is comparing kinematic against control, chit chat against control. This is my main effective trial. And down here, these are my interactions, comparing kinematic versus control, interacting with trial, and then chit chat versus control. So down here, these are our fixed effects. There are random effects, and I skipped the random effects. I need to go back to them. But just so we can sort of preview where the model is going. Unsurprisingly, the model estimates are also not going to be significant. Our main effect was not significant. And so, like I said, the golden standard now is actually not to report these p-values. So these p-values will not even show up if you don't load the package LMER test. But I loaded the package LMER test and I put it into your scripts. So they're probably showing up right now. And I do report them in my final papers. I just do them in addition to log likelihood comparisons.
You could do like the CLAR ANOVA and get the p-values on the ANOVA.
Oh, really?
Yeah.
Nice. All the workarounds to, because we love our p-values and we can't give them up. Okay, before I forget, I need to talk about the random effect structure. I don't like how zoomed out this is though. Now that I see it on the big screen, I want to zoom in for you all. Ooh. Okay, so like I said, these are our fixed effects. This is our model without an interaction. The random effects stay the same across all models. You can test whether random effects themselves improve model fit by removing them and doing likelihood model comparisons. This is specifying random intercepts. So this is the syntax of random intercepts by subject. This is the syntax again, but now random intercepts by item. I should also have this. The reason being, when you have a within subject manipulation like trial, you can do random slopes within subjects, and in this case, also within items. It's possible that I didn't do that for this paper because it didn't converge, or because I didn't know better at the time, which does happen in hindsight. So if you ran the model before I just loaded it, it would have run almost instantaneously because it was very simple. As soon as you add more random effects, it's going to be a lot slower. And so we can see, oh, hey, okay. So it isn't because I just forgot that I should put trial in there. We were not able to include trial as a random slope in these models. And that's, so we have singularity in the model. And this is usually where you start simplifying your random effects. And this is a problem with LMER generally. And in theory, I have been told that Bayes doesn't have this problem, but learning new statistics is hard. So we're just going to avoid the problem. Okay, what's the next phase of this analysis? I then create what are called reduced models to compare against my full models. And I do want to actually, first, I want to clarify, if you look at the summary of model 1 versus model 2, the reason my stats teacher taught me to do it this way is because as soon as you introduce interactions into your model, these lower order effects become partial. Essentially, the variance gets shifted all around. And so for beta estimates, I like to report from my basic model with no interactions, these sort of main effect trends. I report all models, to be clear, but I like to start with this because it tells you essentially, if you are not considering an interaction, where the variance is being accounted for and where the differences lie. And then you introduce your interactions, and now you'll see that these lower order terms, these condition trial effects here, they will change. They might get moved around because the variance is being redistributed in the model. That's not a bad thing. It's just when we're interpreting models, we need to know about these different layers and sort of steps. So I create reduced models to compare against my full models. So the first of these is just trial, and I'm going to compare it against my first model, which had trial and condition. So essentially, this is my model without condition. And then if you run an ANOVA, it's going to tell you whether the effect of condition is significantly improving the model fit. And this is, again, the log likelihood model comparisons are the new golden standard, what's being reported. The second one here, same idea, but this time I took out trial, and it'll tell me whether trial improves fit. And if we look at this, we will see. Oh, you know what? Say again? I'm sorry, can you say that again? Null model? No, I do not have a null model in this example. I am comparing, in this case, model 3 is exactly the same. I copied the code quite literally from model 1, and then I delete the fixed effects. You only want to take one thing out at a time. So I've gotten rid of condition, and I am comparing these two models. When we do this, it's going to tell us whether condition improves fit. It super duper doesn't. When we look at trial, it super duper does. And this is going back to yesterday, just a reminder, trial is always going to improve model fit in pupillometry models, so you should always include it. It's going to account for a lot of variance in your model. It also can help you to avoid potential confounds, comparing across conditions, you know, just, it's just good to cover your bases, in other words, so. There is one parameter different. This trial has been removed in this case. That's what we are testing for. That's actually the intention is purposefully to remove trial. That's changed 1 degree of freedom. And so this is telling us whether trial being added to a model will improve that model's fit, whether it counts for a significant amount of variance in the model. No. No, so I mean, if we go back to the comparison with model 3, yeah, condition does not. And also adding more parameters to a model does tend to improve, it tends to make p-values look better, but there are built-in penalties for having a lot of parameters in your model. Okay, what are we doing on time?
What did you want to have when you have like a gazillion interactions?
Do no interactions, two-way interactions,
Two-way, three-way.
three-way interactions, yeah.
Richards.
Yeah, that, is that how you do it too? Yeah, okay. I know, I get a little nervous because I'm like, this is how my stats person taught me, but
Okay.
everyone's a little different, but. Okay, the PPD, the peak analysis, exactly the same, but we're feeding in different values. So I'm gonna skip over explaining the models and we're just gonna look at the summaries. Trial, once again, significant. The interaction has more going on, but when we compare model 1 and model 2 for the peaks, it's like marginal, so it's not significant in this case. So we can then visualize this. So moving on to code chunk 12. This is the actual code for how we made the figure from the paper, which you can of course take and repurpose for your own needs. A lot of the times if you're doing peak and mean analyses, you won't be plotting scatter points over trial. This is, specific to our analysis. Every analysis is going to be different. You might want to do box plots like I did at the beginning. If you're expecting a really big difference between these two groups, you would probably put up box plots. You see a lot of bar plots for mean and peak analyses as well, and for people doing ANOVA. So there's a lot of them in the literature. So this is showing the trends, but none of this is significant. Just to point this out, there is a significant decrease in peak and mean pupil diameter over trials, but it does not interact with our intervention. That is the end of my mean and peak section. So before I move on, are there any questions lingering in our minds? Okay, so let's move on to curve fitting. Let's say you want to do curve fitting instead. You're going to have some options. I already told you quite a bit about these, but this is a bit of a reiteration. Growth curve analysis, I highly recommend Dan Merman's book. I have just a couple of different approaches to my random effect structure. Excuse me. So if you notice differences, I do what my stats teacher told me was correct, not what is in this book. He does some interactions within the random effects that I do not typically include. Generalized additive modeling. This is the go-to paper. This is where you start. If you're doing it for pupillometry in particular, this is going to be like the how-to that saves your life. As I said before, the reason you might want to use GAMs is if you have a really complex model shape you want to fit. And also, we're going to talk a little bit about what's called autocorrelation. This is something that can increase your chance of type 1 error. This is a problem with growth curve analysis. It's actually a problem with LMER, like the LME4 package. It doesn't give you the option to specify something to correct for this. Small note for those who are very interested in doing growth curve analysis and do want to correct for this. If you use the NLME package, which is the predecessor to LME4, it will let you correct for autocorrelation. I did this whole deep dive when I was a PhD student trying to do this. The drawbacks are there is a reason LME NLME was replaced by LME4. There are things you can't do in the structure, like the syntax for your random effects is much more limited. And so there are trade-offs. But if you have questions about that, I'm happy to chat more. GAMs also, the big drawback to GAMs is they're conceptually far more complex than growth curve analysis models. By this, I mean a lot of us in the newer generations of scientists are being trained in linear mixed effects regression. So we're already familiar with the LME4 package, the syntax, how to do this. And so making the leap to growth curve analysis is going to be way easier for you if you have that background than GAMs. GAMs have a little bit of different theory behind them that I'm not going to get into today. I do recommend this paper. There are also some great like tutorials online that are like the very statsy side of GAMs. But essentially the way GAMs work is pretty different. They're like making all of these little tiny models and adding them together. That's why it's called generalized additive models, which is pretty cool. But the statistics behind it is far more complicated. So if we go back to the same data set, like I said, we analyzed it two ways. We did growth curve analysis. And so let's look at how this growth curve analysis was implemented. First of all, a window was selected, and this was selected in order to maximize the polynomial shape of the data. By this, I mean this is a fairly cubic shape. It's not a perfectly cubic shape, but that's okay because growth curve analysis has a little bit of flexibility. But when I say polynomial basis, I mean it would be very hard to fit something that has sharp peaks and then a soft peak. That would be basically impossible with a single growth curve analysis model. For growth curve analysis, there is some prep in code chunks 3 to 13 that I'm going to skim over, and Dan Mermin goes over it in his book quite clearly. You create what are called orthogonalized polynomials. These polynomial functions are going to be fixed effects in your model. So the same way that condition can be an effect in your model, poly1, this linear line, is going to be put into your model. And how this ends up making this nice curvy shape is something that you're going to hear more about in the next session from Julieta. She's made a Shiny app in R that's like super cool, where you can like mess around with the parameters and see how it affects the shape. So you can really conceptualize what's going on behind the scenes in order to make this shape. And so this quick plot, this is something I do before I look at conditions. You can fit a growth curve model that has none of your condition information. It is just your time course of data, and you can confirm that you can fit this shape of data with growth curve analysis before you go into the analysis. And I think this is a good step to take. And as far as determining if it fits, this is based on visual inspection. So this is a bit arbitrary. But if you do not know whether it's going to impact significance, then we're still putting off those researcher degrees of freedom. So let's take a look at some of the growth curve analysis code. This is building on our knowledge of linear mixed effects regression and the LME4 package syntax. Julieta is going to do a deep dive for an hour with us on growth curve analysis. So I'm just going to give you surface level discussion of this. As I was saying, polynomials, in this case, I have 3. So this is my linear, my quadratic, and my cubic shapes have been put into this model. I did not attempt further. You can do quartic, you can keep going. Polynomials keep going, and you can do more. I usually stop at a cubic shape because that is usually good for fitting the shape of my data. And then I have the other effects I was interested in. This is just like our mean and peak analyses. The random effects are more complex. Anytime you are doing time series data, you want to, if at all possible, include time, which is a within subject effect, as a random slope. And so that is what this is doing. It looks a little weird because I didn't put the word time here. And in fact, you'll notice that the word time is nowhere in this model. And if you remember, time is a column in our data set, so that might be very confusing, but if you go back and look at the code, we generate these polynomials using the time column. So in a way, they are time. And this is where they're a little bit funky, and conceptually, it's a little bit weird. But this is essentially our time variable and also our shape variable, and it's all in one. We want them as random slopes within subject. I also wanted them as random slopes within item. This is the real model from the real paper. So I apologize for showing you a complicated example, but it can be a learning opportunity. Originally, I wrote this same line for random intercepts, random slopes of poly 1, poly 2, and poly 3, all within subject. I wrote the exact same thing for items and it would not converge. This happens a lot with growth curve analysis. It's really hard to converge the really complex random effects. The first step before you start getting rid of your random effects that you wanted is you can remove the correlations among the random effects. So if you didn't know about this, it's a nice first step so that you don't have to get rid of this entirely. In many of my papers where I've used growth curve analysis, I have to drop a polynomial from the random slopes, and it's not ideal. I've also seen a paper, it's not really a paper actually, it's like a discussion forum of someone talking about how we can maybe fix some of the autocorrelation type 1 error issues if we have really complex random effects in growth curve analysis models, which is a great idea, but it is almost impossible to implement because your models will not converge. So for example, I should also have not condition because that's between subjects, but trial is within subjects. I could have random slopes for this and that would be, it would just not converge in this case. So that is my first growth curve model, which is once again, same style, all fixed effects, no interactions. Model 2 starts to get a little crazy. I have my interaction I'm very interested in, which is condition by trial. And then I have interactions between each of these shape terms and condition and trial. So there's a lot of interactions going on. This is going to allow the model to, for each condition, create a different shape of curve. To a degree, again, we're stuck with the polynomial basis, but for one condition, we can have a very cubic, and for one, we could have more of like a quadratic, for example. So it's allowing it to vary by condition. It's allowing it to vary by trial. So over the course of these 80 trials, the shape can change too. This is important because if you imagine the amplitude deflating over the course of trials, it's inherently going to change the shape of the pupil response. It's not just we had a cubic shape and it's just falling downwards statically. It is truly changing the integrity of the shape.
What's the -1 in the random?
Oh, yeah. So this is how you remove the correlations between random intercepts of item and the random slopes of these polynomials. So I still have random slopes for each of these polynomials, but if you look at the model summary, usually in your random effects section, it tells you the variance, standard deviation, and then it gives you a correlation of all of them. You can see it's missing because I have intentionally removed them. So when I tried to do it the typical way, what typically happens is you will get an extremely high correlation, like 0.95 or higher, I would say, will probably break your model. And so you can tell, even when a model doesn't converge and it says model singularity, I can't do this, you can still look at the model summary and usually you can figure out this is a pretty high correlation, but there was probably one that was even higher in this case. And so the first step I took was getting rid of those correlations. Yeah. But that way I still have my polynomial slopes within items. Yeah. Yeah.
No, very clear in my head. When you're using polynomial into your interaction
Mm-hmm.
fact, or into your interactions, then if you do get an interaction with the polynomial,
What does it mean?
Yeah.
Yes.
you interpret it.
This, yes, I said growth curve analysis was going to be easy, but when I said easy, I meant easier than the alternative. It is incredibly hard to conceptualize this. And again, I'm going to postpone this to sort of Julieta has made this app where you can look at how this turns out differently. And she'll show you, you can plot the individual curves to see like if there's a significant interaction. With poly 1, it's usually pretty straightforward because if we go back to our polynomials, it's basically just linear. And so if we think of our pupil response, it's usually like a nice peak over towards the right. And so this is usually how steep it is going up to that peak. So it's the most informative interaction and it's very conceptually easy. If you have a higher peak in one condition, there's going to be an interaction with that slope. Quadratic and cubic, differences in shape are happening. Reviewers often get frustrated with me when I don't describe in detail what that means, but it's incredibly hard to do so. And the really important thing conceptually, and this is the same for GAMS, all of these fixed effects, when we're doing fixed effects models, they're additive. And so we're specifying a shape for this line, a slope of this line. We're gonna add this green one. We're adding them all together. And so what we're doing is we might flip this green one entirely upside down if it's negative. But we are going to be adding these lines together to come up with our fancy shape, which isn't actually a cubic polynomial. It's more of like a sort of straight cubic polynomial. That makes sense? Yeah, okay. Yeah, it's a lot to digest.
They are just, I thought you were gonna get into comparing them. That's not the point of having polynomial three. They're just
They're adding on top of each other.
They explain better your data.
Mhm.
You can describe that, but then, yeah.
Yeah.
Then also, yeah, why would you?
You have to,
Yeah, why would you have an interaction with one and over the other and?
so if you don't have interactions, then you cannot allow the shape to change by trial
Depending on the trial.
or condition. Yes. So it would mean you would just have the same exact shape. And if in the control condition, it's a higher amount, it would shift that same exact shape up. But that's not reality. That's not what it looks like. Yeah. So I'm going to stop there for growth curve analysis, and I'm sorry if it's a little dissatisfying, but there is a whole nother session on it. And what I really want this session to be is a compare and contrast across these three main approaches. And the third approach is not on this slide just yet. It's going to be GAMS. I forgot to do the summary of what we just talked about. Let's do that first. Yeah.
So that model you showed us with the minuses, and that's the final model.
That's my final model.
Okay,
Yeah. So that's the final model summary here without the correlations. Oh, I didn't even talk through what we found, but I'll summarize it on the next slide for you. What did we find when we did peak analyses? Non-significant. And by this, I mean the main effective trial was always significant. It's the interaction with our intervention that we thought was going to change the world of pupillometry and is not going to change the world of pupillometry. Peaks, non-significant. Means, non-significant. Growth curve analysis. This is a fun one. Social breaks actually help. Technically. I mean, can you say they really help when the fatigue effect is still ginormous? It's a genuine important question. The kinetic breaks made things worse. So instead of reducing the distance between the first and fourth quartile here, this distance is larger than in the control condition. And if you remember from yesterday, I was talking about people got really excited about the kinetic sand. So they're more aroused in terms of like tonic baseline arousal. And so they had larger pupil response to start out with. That leaves more room to change perhaps. Regardless, if you're trying to get rid of this change over time, giving people kinetic sand is not going to help you. So the mean pupil diameter analysis and the growth curve analysis actually do tell the same story. This one was non-significant, but in the same direction. But it's worth noting that the effect size was clearly much larger in the growth curve analysis. Bigger effects or more significant p-values is not always inherently good. I want to clarify this. We also have to remember that growth curve analysis is prone to type 1 error because of autocorrelation in the data. But I will say the way we prepared our mean and peak pupil diameter was extremely noisy. You can see how noisy it is. Whereas in the growth curve models, we weren't essentially picking up on random spikes in the data. We're sort of smoothing it out and getting this nice plot on the right. So in this data set, growth curve analysis was arguably more effective. But long story short, our conclusions in this paper were that none of these breaks are helpful. The social breaks, technically significantly better in that one analysis, but like long story short, you can't just give people breaks and get rid of this effect of decreasing amplitude over trials. Now we can transition. Let's talk about GAMS, because this might be a method that you want to use, and there are lots of good reasons you might want to use it. We didn't use GAMS in the paper we were just talking about for a few reasons. The number one and most important reason, which is a genuine consideration for anyone who is starting out, is I didn't have a firm understanding of the statistics. And I had no reason to believe that I had to use GAMS for that data set, if that makes sense. If you have reason to believe that you need to use GAMS for reasons that will become clear over the next section, you have really complex interactions, you need to control for gaze position, then you will need to use GAMS, and so you will be forced to learn. In my case, I was not forced to learn. My data had a very polynomial basis, as we saw. It was really well suited to growth curve analysis. The research design was also fairly simple. The most complex thing I was looking at was that interaction of condition and trial. Again, all of this very doable with growth curve analysis. If you are getting started with GAMS and pupillometry, these are the top resources I would recommend. This is the how-to paper. The second one is just an example paper that I like. It's a speech perception paper, and it has some complex interactions in it. So it's a really nice example to see GAMS in action. But I don't have access to that data set, so we're not going to be analyzing that. I recommend that if you want a published paper to go look at. But the data set that I have provided you with today for this introduction to GAMS is a data set you've already seen quite a few times, where we are looking at listening to 2 sentences in a row, where you have to either switch between your languages, Basque and Spanish in this case, or you do not have to switch between your languages. And this is listening. Sorry, this is not a speech production task. This is listening. So this is the same data set that I've talked about a few times now. So we can go ahead and get started. Hop on down to code chunk number 22. I know I skipped over quite a few of them, but if you want more details about stuff I skimmed over, you're welcome to go back and look through. Oh, and actually, just a heads up, if you're in Markdown, you can click here and you can very easily skim down to data set number 2. Yeah, so if you've never done that before, I have it marked very clearly where data set number 2 starts. Okay, so let's, yep, go ahead and load the data set. This might take a second because it is a lot of data, but it's pretty, and it's pretty cool. I'm very excited about this data set. You're going to see like our first 36 participants, which is Jimena's master's thesis, but we're going to get 60 because with GAMS, you want as many participants as you can justify. Because there's a lot of, long story short, there's a lot of statistical penalties for how flexible GAMS are. So you have to penalize somewhere to ensure you don't get type 1 errors. So more participants is definitely better. Go ahead and get a summary of this GAMS data set. You're going to see there's a lot here, and some of these columns might be sort of familiar because you processed some of the first participants in the earlier sessions today. Although I've given you the full 36 participant data set here. So we have subject, we have a condition. There are actually 3 conditions here. We're just going to ignore conditions today because I didn't want to make this session overly complex. But we can see there is a whole bunch of information in here. We are not going to look at it all. If you're curious, you are welcome to create more complex models using this data set though. The first couple of things we need to do. There are 2 steps for setting up for GAMS that are explained in the Van Riech paper. The first, we're going to only, oh, sorry.
Yeah, I'm getting.
The path is wrong, so you're gonna have to add. So
Well, where is it?
Deepest apologies.
it's in pre-processed data. It's session 4 example data, pre-processed data. Save underscore pre-processed.
Yep.
Yeah.
Oh.
But I'm also still getting
Yeah,
that issue.
but I
So-
don't have it, like, it's not in the folder. Oh, maybe because she's, when did you just download the folder? Maybe it's an updated, like, I think yesterday, maybe.
Yeah. So try to go download it again.
Yeah.
Let me, oh, no, it's okay. Thank you for saying something before I went on. Let me see.
Yeah. I still get it.
It should be in the folder online. And you know what? It was uploaded at a later date, so that's probably why you didn't get it. May 25th. So.
It's online.
I'm having a hard time with paths. I think I,
No, and it's telling me warning in scan, into file without quoted string, so maybe there's a typo in the file, and I can open it up and see. I don't know if anyone else is having the
But
same
yeah,
problem.
mine is thinking.
Like there might be a set of quotation marks.
Why sometimes?
are you sure it's not the code you're running?
I'm pretty sure because I checked to make sure that R is finding the
Okay.
right file,
Oh,
and
mine
it says,
is
yes, I
fine.
can find the file.
Mine is good.
Okay.
Maybe try re-downloading it, right?
Yeah.
Oh, I didn't get this error, that's the thing. But I have a very weird question. Why silly?
Go for it.
I know that when you have the chunks in R markdown, like you can do it in chunk,
Mhm.
but if I go one by one, sometimes it doesn't like it and it wants it in chunk.
Yeah, this is why I don't like our markdown,
Yeah, what
but I don't know. My answer is I don't know. I actually,
version? How do I know? Oh, 4.21.
Yeah, that's what it should.
is it a PC? It's a PC issue. So deepest apologies to my PC users. And you know what? This actually rings a bell because Jimena has a PC and I had to reprocess the data for her at one point. Actually, do I have a version of the reprocessed data? I'll look it up in just a sec.
Oh, wait, it says something, warning there. But it's a warning, I don't think it's that.
Okay, I'm going to upload one that I made that worked on Jimena's computer, which was also a PC. It's called Vic Preprocessed, no quotes. I'm just gonna put it in that folder. So instead of the SIA's preprocessed data set, try opening this one. But it'll take a minute to upload. So PC users will be a little bit behind.
Keep fire knows.
Hmm.
No, what is going on?
Okay, I'm gonna trudge forward, apologies, but just so that we can hopefully stay on schedule. The first thing you have to do is, and there's great instructions in the Van Riech paper. Again, I'm just gonna keep referring you to that paper. It is necessary for GAMS to set up your factors a very specific way. So in this case, we're gonna look at an effect called switch that has 2 levels. And I am here changing them to 1s and 0s, and I'm relabeling it is switch. If it's a 1, then it was a switch trial. If it's a 0, it was not a switch trial. The next thing you have to do for GAMS is add what's called a start event. This is sort of weird. I've also been getting weird warnings on my R. So if you see a warning for the purpose of the workshop, yeah. Wait, oh, hold on, I skipped steps. Wait, did you? No. Okay, yeah. I have been getting this warning for the purpose of the workshop. We can ignore this because we can still process the data set. And I need to look into this because this is like code straight from Van Riech, and so I'm not sure what's going on here. And then because GAM models, okay, another consequence of GAM models being able to fit anything, they take forever, and they take a lot of RAM. So you probably cannot run them on your laptop. Some simple models, but not the slightly more complex model that we're going to look at. So in code chunk number 23, I want you to load in these models. Code chunk number 4 will show you how to build these models from scratch, but I do not recommend you run this on your laptop right now because it might crash your R session if you do not have adequate RAM. Some people might have RAM on their computer to do it. And also, while we're loading this up, were people able to download the no quotes version?
Without saying switch, saying object switch not found, or that's the same error that you were getting with the mutate. Can you do the console scroll up a little bit? So that
I didn't really check that file. There's a chance that the switch column doesn't exist.
wait, let me see. Yeah, I don't see a switch column.
Yeah. Is there anything that looks reminiscent of switching?
What does the data look like? Like what's in the column?
Ta-da.
What is it? Oh, these. I don't know if that's in the big, that's okay.
It's okay. You know what you can do probably is if you're determined to look at the data with us, you can just plot it with no effective switch. I mean, you can you can run this model and just comment out is switch. You'll on your machine in particular, you can probably do it, Daphne. So and then you'll just fit a smooth function with no effective switch. So if you have loaded your models, you can take a look at GAM model 2. So I am trying to summarize it right now. It's a lot of work for my computer because even the model itself, opening it up, takes up a lot of space. So you can see my computer is telling me it has 1 gigabyte of usage right now. Okay, GAM models. There's a lot of details that I'm going to skim over, like how you pick the K value, which still perplexes me to this day. But let's look at the model syntax real quick. What this model is saying, it's a lot like LME4, LMER, but a little bit different. So we're using what's called the BAM function. We are predicting pupil. That's the tilde. So this is the same syntax here. We are creating what are called smooths. This is the language, the lingo that we use for GAMs. So this is how we create any shape in any way we want to. We're doing this over time. This is like the most basic thing you need to enter. We're looking at this over time. We then want to make a distinction between switch and no switch trials. So this is our main effect here. We then have random effects, and we're specifying them by subject. Every subject can have a unique shape, a completely unique shape, and it's specified in this one line of code. So in this way, we do not have the random slopes within. You can add more layers to the random effects, but for our purposes, we're just going to focus on, you have a random smooth by subject, which means every subject can be completely uniquely fit. So if we go back to looking at the code output, the big thing that I want to clarify here is what p-values mean in model summaries for GAMs, because it is not what p-values would often mean in linear mixed effects regression. Here, this main effect of is switch is significant, and it is telling us that the smooth line it fit for the is switch effect is curvy. That is what this p-value means. It is significantly different than a horizontal line with no curviness. This is the weird thing about GAM models. They tell you how wiggly they are in their model summary, which maybe is useful for some research, but it's not going to be useful for our research. So that is a really important thing. Don't get excited about, I mean, technically, if you see that, for example, in this case, it's not significantly curvy for the by subject, which is a little surprising, actually. You know, you could consider dropping things from your model if they don't improve fit, because it means they aren't changing the shape of these lines based on this effect you have added. So that's user preference because some people want to make it maximal, put everything they possibly can in the model, and some people don't want to put too many effects in the model.
And what's the reference in this model specifically? Right, so that's the reference as time.
So is switch, is that binary 1 versus 0? So switch trials are 1s, non-switch trials are 0s, but this is not, it's not like dummy coding in the same way.
But what's the line before it, though? That was my question.
Oh, this one?
Yeah,
Oh, this is just your over time. You're just saying, I want to make a curve over this time course. If, for example, you weren't doing pupillometry, because there are people who use GAMs for things other than pupillometry, you might want to look at performance over trials in a reaction time task. This could be trial instead. This is our continuous variable that we are fitting over. K is it's sort of degrees of freedom E. It's how wiggly your line's allowed to be. And I'm going to refer you to the Van Riech paper because it feels very mysterious to me as far as how you pick a K value.
And you mentioned before that when you look at the summary, the p-value is not significant, means that if for subject, for example, means that the curve is not,
Yeah, they aren't changing much by subject.
okay, so instead of maybe you might think of dropping that. So would you compare models the same way you do it with linear mixed effect models?
Yes, so this is a great question. You can do model comparisons with GAMs. Yes. You can, and I would recommend it. There are pros and cons. The con is just time. You're going to have to fit so many of these models, and these models will take an hour often. This first model will not take that long, but the very next step we're going to do is adding the autocorrelation correction. As soon as you add that, as soon as you add anything complex, it's going to take you like an hour. And so you can do model comparisons. The Van Riech paper goes through how to build your models if you're doing model comparisons, because the other thing about GAMs is you can build your models different ways to get to the same outcome. And so you have to choose how to code your data, just like you do for any regression analysis, but definitely look at their paper for the exact rules of how to do it. Yeah.
For anyone that has trouble with the files, and the VIC file works for me, but also if you just add at the end with the saves one, if you add another argument, quote, QUOTE equals, and then double quotes, just one set of double quotes, that fixes it.
So at the end of this?
Yeah.
And what is it? Quote equals?
Quote equals, and then just a set of double quotes with nothing in.
Okay. So for those of you who couldn't load it. And it's specifically for PCs. Always a delight to discover.
the wonders of PC.
Okay, that's our first model. The next thing you're going to want to do in any analysis, oh, I completely skipped over explaining what start event is. This is the weird GAM specific thing where we're telling it where the start of each trial is. So that's just a little true term, if you're curious about that. So, to make our, I'll just do it from R. So we have this first model, and then this second model, we are adding in the AR component. So there's a couple of things being added to the model here. This is fairly standard. What you're doing is essentially you're assessing the first model that you built that did not correct for autocorrelation. You're feeding some information into your second model, and this time you're telling it to use AR, which is autoregressive function. There's not an F there, but that's my memory. I think it's supposed to be an autoregressive function. This is going to correct for autocorrelation. Once we have this model, you can take a look at this model if you've loaded it in. This model is, it's going to be big.
We're not running this, right?
No, don't try to converge the model. I was trying to make a summary of it, but even that is a little tough. You'll notice that most likely not a lot has changed in the model. It might change I wonder, does it change no, yeah, not a lot has changed. In fact, Oh, I summarized the same model twice, so that wasn't very useful. That's all right. What we're gonna do, scroll down to code chunk 25. The whole reason, one of the big reasons to use GAMs is this thing called autocorrelation. So I want to show you two plots. The first is autocorrelation. Here we go, autocorrelation function in GAM model 1. This is where we didn't correct for this issue. What is autocorrelation? This is any type of time series data will have this problem where you have time points 1, 2, 3, 4, 5, and you have a curve going along these time points. The values at 1 and 2 are always going to be highly correlated. The values at 2 and 3 are highly correlated. So what this is plotting is it's called a lag function. So this first line is the correlation with itself. It'll always be 1. So, the correlation with the current value when the lag is quite literally 0. Correlation with yourself is always going to be 1. Correlation with the next value, very high. Correlation with the value after that, very high. All of this correlation across your time series, what it can do is increase your chance of type 1 error. By specifying that AR component in that second model, we dramatically decrease this. This is sorcery. I don't know how this works, but it's great. Don't worry about the fact that 0 is still enormous. It's the 0 is always correlating with itself. You're never going to get rid of that first line. This is phenomenal. We have mostly removed autocorrelation of residuals from our data. We're running short on time, and I want to move on to the fun part, which is making plots. I have code for you here so that you can make GAM plots. If you have loaded the models, you can make plots a little bit different than LMER. GAMs have their own world of plot functions that will take your model. It doesn't take your data. It takes your model and it'll make plots for you. What I really like about this is you can make difference curves. So the first plot here, plot smooth, is going to give you our two conditions, nice and beautiful here. This is our switch versus no switch, and we can see the complexity of these lines. These confidence intervals are meaningful here, and we can actually plot the difference between these two lines, in plot 2, and it will tell us where these lines significantly differ from each other. This red mark going along the x-axis is telling us where they differ. It's beautiful, it's very lovely, because in contrast with something like growth curve analysis, earlier you were asking, what does the quadratic interaction even mean? And it's like really hard to interpret. And you don't really do these difference curves in this way. This just cuts to the chase and says, these lines are significantly different, but only in this section of the data. So you can look across plot 1 and plot 2. This can be really powerful. You can imagine if you had multiple peaks in your data, it could tell you that 2 of the peaks are not significant and the last peak is, for example. Really, really powerful. It'll also spit out some information when it makes that plot diff function, and it'll give you the numeric area where the points are different from each other. So you can look at the time window. So I said 2000 just by looking at the plot, but technically it's 2011. So you can get the specific number to report in your final paper as well. So on the subject of GAMs, GAMs have multiple ways to determine whether effects of experimental manipulations are impacting the size of the pupil. The number one approach is visual inspection of difference plots, the plot that had the red line along it. I will say, I don't love that as like the bare minimum. I think we need to be doing model comparisons, and you'll see some papers that don't report model comparisons because they are so time intensive, but I think we should be doing model comparisons because it is what we're doing in linear mixed effect regression and so on and so forth. You can also inspect the model summary statistics. As I was saying, these are often not informative, so don't be tricked into thinking your effect is significant. It might just be telling you the effect is very wiggly, which is a little hilarious, but But Van Riege goes into detail of how you can build your models if you specifically want your summaries to be more informative. So there is information about that. Some warnings and notes. The first one, I want to very much stress, if you don't fit your GAMS model correctly, the difference curves may be misleading. And this is the other reason I do not care for using the difference plots as the primary source of determining significant differences. As an example, because it's always good to talk about when we make mistakes and be open about that, I wanted to use GAMS on my dissertation data set, which was actually not pupillometry. It was during COVID, so it was online data collection, and I wanted to look at change in performance over trials because I thought I was going to have some really interesting stuff that needed to be fit with GAMS in the task I had designed. I collected a preliminary data set. I did a GAMS analysis and I put it into a grant and it looked wildly significant. The lines were beautiful. The difference plots were fascinating. And then I discovered I had done my random effects completely wrong. And these difference plots were saying everything was significant and cool. And it ended up being none of it was significant and cool. Now that was a preliminary data set. It did go into a grant, but it was a preliminary data. So it wasn't the end of the world. But gosh, was I happy that I didn't go to publish that data set and then discover I had done it wrong. So be very careful with how you build your models because you might make assumptions, especially if you're trained with linear mixed effects regression and the LME4 package, you might make assumptions about how things are working. And those assumptions may not actually map onto GAMS the way you would expect. As I've already said, model comparisons can be very time intensive. Very computationally intensive. If you're going to do this at BCBL, you're probably going to have to use the server to do this. And those model summary statistics sometimes are less informative, but you can make them more informative. Look at page 12 specifically if you want to do that. So let's get to the summation slide here. What do you use? I told you you can do all these different things and now you have to make a decision. Let's discuss pros and cons. Summary statistics. I'm going to be honest with you. I almost never use these. The reason we use that data set today is because it's the only data set I have ever done them in, because I was pushed to do them because that's what other people had done. Just because other people have done it doesn't mean that you necessarily should do it. That being said, I did note as a real criticism of my prior work, I could have done more to clean up that data because I could have gone through and inspected every trial and thrown out bad trials. I have seen that reported in some more recent papers of people really carefully going through with a comb to clean up their data before extracting peaks and means. And I imagine that could make a very meaningful difference. So if for some reason in your data set, it makes more sense to do these sorts of summary statistics, then it doesn't mean that your data is going to be bad or inherently noisy, but you should take more steps than we took in this tutorial today to clean your data, is my recommendation. Growth curve analysis, I have used very frequently. Almost all of my papers, I used growth curve analysis. I found the syntax and underlying statistics intuitive, but that was because of my statistical training in my PhD. I like it. It has limitations. Obviously, type 1 error is like a really important thing. And I think everyone who's using growth curve analysis is just sort of, you know, whatever the expression is, like we're just sticking our heads in the sand a little bit. Generalized additive mixed models will fix this. They are conceptually more complex. Be careful when make sure you're really developing your understanding of the underlying statistics. Computationally intensive, I've already said all of this. Difference plots, super cool. Highly recommend them. I mean, for putting it in a paper, it's just so informative and easy for the reader to understand a difference plot. But I think we should do model comparisons as well. And you can fit all sorts of complex shapes and interactions that you might not be able to do elsewhere. The other thing about GAMS that I actually haven't said yet, you can do really complex things. So if you want to do visual world paradigm at the same time as pupillometry and you have XY coordinates, look at the paper I recommended, Peretta and Tucker. I think it's the Peretta and Tucker paper. Hopefully I'm right about that. They put X and Y coordinates over time into their GAMS analysis. And then you can make like heat maps. I actually don't like heat maps. I find them very confusing, but you can do incredibly complex things. So if your design requires there to be essentially looking around the screen, you can statistically control for that. You can statistically control for just about anything with GAMS, even if it is a continuous variable. And that is extremely powerful, especially if you are working with special populations or specific design that's basically putting you in a corner with pupillometry, and you feel like you need to control for something like gaze position in particular. And that is the end of my slides. Questions first?
The thing that I said, it makes it read it incorrectly, but it reads it weird and it's giving a different answer. So I would suggest not.
Let me scroll up here. X-nay on the quote A, that did not work. So apologies to PC users, something about the data set was not prepared well for your computers. You should still be able to, with the PowerPoint, come through and look at what you should have been able to get. So you can backtrack and look at that. I am going to recommend that we take